Scars from a past Earth impact. Weird structures near Earth's core may be the scars from a primordial interplanetary collision. A collision with a Mars-sized planet 4.5 billion years ago may have left a permanent impact on our planet's deep mantle, scientists say. We have an artist's impression of the Hadean eon, when early Earth may have been struck by a renegade Mars-sized planet. We do have scars from the Great Bombardment. Now, a group of mysterious ultra-dense structures just outside Earth's core may be the remnants of an ancient interplanetary collision, according to new research suggestions. These strange structures are known as ultra-low velocity zones, ULVZs, because seismic waves generated by earthquakes travel about 50% more slowly through these zones than through the surrounding mantle. So that means that the ULVZs are also much denser than the rest of the mantle and possibly made of heavier elements. It's hard to say anything for certain about these dense blobs of rock because the ULVZs sit nearly 1,800 miles or 2,900 kilometers below the Earth's surface, one group clustered deep below Africa and another below the Pacific Ocean, where the rocky mantle and liquid metal outer core meet. That's far too deep for human eyes to see, of course, so only seismic data can offer clues about the size, shape, and structure of these ULVZs. But now, using new computer models and fresh seismic observations from deep below Australia and New Zealand, researchers may have added an important piece to the ULVZ puzzle. According to a study published December 30th, 2021, in the journal Nature Geoscience, these zones are not uniform structures, but rather seem to be made of layers of different materials that accumulated over eons. The most surprising find is that the ultra-low velocity zones, ULVZs, are not homogeneous, but they contain strong structural and compositional variations within them. This is what the lead study author Surya Pachia said, postdoctoral scholar at the Australian National University. He said this type of ULVZ can be explained by chemical variations created at the very beginning of the Earth's history, which are still not well mixed after 4.5 billion years of mantle convection. So they haven't been mixed, they're still there. Mantle convection is a process by which the solid rocks in the planet's mantle slowly move in accordance with the heat currents. After their computer simulations showed that the layered or mixed structure was likely within the ULVZs, the researchers suggested a possible origin story for the structures, a story that starts more than 4 billion years ago, around the time early Earth's rocky crust first formed. And beneath the surface, heavy elements like iron were sinking towards the planet's core, while the lighter elements like silicon rose towards the mantle. This origination all went haywire when Mars-sized planet known as Theia slammed directly into early Earth, an ancient cataclysm that researchers call the Great Impact Hypothesis. The collision may have scattered enormous amounts of debris into the Earth's orbit, possibly leading to the formation of the moon, they said, that's a theory, while also raising the entire planet's temperature and creating a large ocean of magma on the planet's surface, Pachai said. Various rocks, gases, and crystals forged during the collision would have been scattered through this magma ocean, the researcher said, but not forever. Over the following billions of years, heavier materials would have sunk towards the bottom of the mantle, followed by lighter ones, eventually creating a densely layered structure of iron and other elements at the core mantle boundary. As the mantle churned over the ages, this dense layer would have separated into smaller clumps spread across the lower mantle, effectively giving us the ULVZs we know of today. The scenario may not explain the source of ULVZs, the researcher said, as there is also some evidence that other phenomena such as melting ocean crust sinking into the mantle could explain ULVZs. But the team's model shows that the giant impact hypothesis reliably explains how the dense layered zones could have been created. This is by Brandon Spector on Live Science. Please leave your comments and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.